As I discussed earlier, so we'll be seeing the basic laws that are used in this machines. So let us start the class. Okay. So basically, we need to first understand that the first chapter is called as the AC generator. So first, we need to understand what is a generator. So basic definition of a generator. A generator is a machine which converts mechanical energy into electrical energy. Generator is a machine which takes input as mechanical energy and converts it into electrical energy. So this conversion process is done in magnetic medium. This conversion process of mechanical energy to electrical energy will be done in magnetic medium. So this machine which converts mechanical energy into electrical energy is what we call it as generator. There are various types of generators. As we have seen in the last class, we have two types. Main division is like AC generators and DC generators. You people know what is AC and DC, right? AC is alternating current and DC is direct current. In direct current, the values of the voltage and current will be constant throughout the time period. If we are going to the alternating current, the values of the voltages and currents will be alternating throughout the time period. If you take a given time period, if you take some time, x time, in that x time, the value of the voltage and current, if the value of the voltage and current are constant without having any change, then that type of current is called as direct current. Directly we are getting the current and there is no change in that value of current. If there is a change in the value of current over the period of time, like if it is going increasing and then decreasing and then going into negative and then increasing back to positive, if it happens like that, then it is called as an alternating current. Basically, we will be seeing both the type of machines. Here first we are going to understand what is the basic nature of a generator. A generator in general will take mechanical energy as input and give electrical energy as output. What type of electrical energy is it giving will be depending upon the construction of the machine and all those things. So basically, it will take mechanical energy and it will give us electrical energy. This type of machine is called as a generator. In the same manner, we have another machine which is called as a motor. Here, in this motor, the electrical energy will be the input and the mechanical energy will be the output. It will be just opposite to the generator. In generator, we are taking mechanical energy as input and giving and taking electrical energy as output from the generator. But in motor, we'll be giving electrical energy and we'll be taking mechanical energy. This is the main difference between a generator and a motor. A generator and a motor. Okay. So all these things, whatever the conversion might be, it might be from mechanical energy to electrical energy or electrical energy to mechanical energy. This all conversion takes place in the magnetic medium. All conversion takes place in the magnetic medium. How and why are we going to the magnetic medium? Let us see. When we understand the fundamental laws, we'll understand why we are going to the magnetic medium. Okay. So basically, there are many fundamental laws for the machines, or in general, these are the fundamental laws for any electrical engineering equipment. So what are those fundamental laws means? Basically, the basic law is Ohm's law, and then we have Kirchhoff's law, and then we have Faraday's laws of electromagnetic induction. We have Maxwell's right hand thumb rule, Lenz's law, Fleming's right hand rule, Fleming's left hand rule. Let us see what they are and how they are why are they being used and what do they depict in general. So if we are using a law, it must have some application, some kind of application must be there. It should give us some kind of information. That is why we are using that law, right? So let us see what are those laws and why are we using these laws. Okay, the first one is the fundamental law in electrical engineering, which is called as the Ohm's law. Okay, the fundamental law of electrical engineering, which is called as the Ohm's law. So let us see what Ohm's law states. Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. So it's saying the amount of current flowing in the in a conductor, the amount of current flowing in a conductor will be proportional to the voltage across those 2 points. They will be directly proportional to the voltage across those 2 points. That means if the voltage is greater between those 2 points, then that means there will be more current flowing from those 2 points. Okay, for this we can take the example of a water. Okay, if you have water which is being flown from a certain period, a certain height, then if the height increases, the amount of water also increases, right? If we are taking a tumbler and we are putting a hole in the tumbler, if we are putting the hole at the very low end, that means there will be only, sorry, at the very high end. If you see this is a tumbler and you are putting a hole right here, that means the water up to this point, will be flown away. If you put a hole at the bottom of the tumbler, that means will be more water will be flowing. In the similar way, if the potential difference between 2 points is greater, then the amount of current flown between those 2 points will also be greater. So that is how this is explained. This is the basic law for any conductor. Okay, so V is directly proportional to I. V is equals to IR. We are introducing a proportionality constant here in order to make sure that our proportionality is converted into an equality. So what is that proportionality constant means? R. R is the proportionality constant. R is nothing but the resistance, which we have already seen. What is the nature of the resistance means? It is the opposing force of the conductor. It is the virtue of the, by virtue of this particular property, the uh, by virtue of this property, the current will be opposed in a conductor. So V is equals to IR is the Ohm's law, and here you can see in the right hand side you can see a triangle. Right hand side you can see a triangle. This triangle is called as a Ohm's law triangle, or you can otherwise call it as a magic triangle, which will give you a relation between voltage, current and resistance, which will give you a relation between a voltage and current. How does this triangle give us the relation between voltage and current means? Like this. If you want to find the voltage, now please mute yourself. 439. Okay. Okay, so if you want to find the voltage, you can just take the voltage and then the other two will give you the formula for voltage. That is V is equals to I into R. Ma 439, please mute yourself. Okay, so if you want to find the current instead of voltage, you can take the current and then it will give you the relation between the voltage and resistance. That is I is equals to V by R. In the similar manner, if you want to know the resistance value, which will give you a relation between V and I, R is equals to V and I. By using this triangle, you can just find out whatever the parameter you want in an easy way. Okay. So this is the Ohm's law. Basically, when we go for the materials, we will describe the device or the material as ohmic device and non-ohmic devices. Okay, ohmic device and non-ohmic devices. Ohmic devices are the devices which will follow Ohm's law. Non-ohmic devices are the devices which do not follow Ohm's law. Basically, most of the uh, most of the devices which we have are ohmic devices. Whereas some materials, there is an exception of for the Ohm's law only in some materials. Those materials are called as the non-ohmic materials. Okay, those materials are called as the non-ohmic materials. The next laws which we need to see are the Kirchhoff's laws. Before going into the Kirchhoff's laws, we need to understand basic definitions of different parameters. For this particular diagram which you are seeing is called as a network. Okay, this particular diagram which you are seeing is called as a network. In this network we have different parameters like a branch. A branch is a connection of an element between two nodes. A node is a junction where two or more elements are connected. A node is a junction where two or more elements are connected. If you can see here, he is showing us the nodes here, and then we also have, he is also giving us what is a branch. A branch is a connection between two of the nodes. Okay, and nodes are the elements, are the points where two or more elements are being connected. Two or more elements are being connected. If you can see in this first node, there are three elements being connected, that is R1, R2 and R3. Whereas if we take another node, let us say this node. If we take this node, what are the elements that are being connected? Means we have R2, R3 as well as the voltage V. These are the elements that are being connected to this node. So these are a point, a junction where two or more elements are being connected is called as a node. A junction where two or more elements are being connected is called as a node. A branch is an element which will be connecting two or more two nodes. Where branch is an element which will be connecting two nodes. Okay. Now, a closed path is called as a loop. A closed path is called as a loop. So these are the element. These are the basic definitions which we need to understand in order to go for the Kirchhoff's laws. Now you know what is a node, what is a branch, and what is a loop. Ma Gautam, please mute yourself. Gautam, mute yourself. Okay, so let's go for the Kirchhoff's laws. So first one is called as the Kirchhoff's current law. Let us see what does this state. Kirchhoff's current law or KCL states that the total current or charge entering a junction or node is exactly equal to the charge leaving the node, as it has no other place to go except to leave, as no charge is lost within the node. So he's saying that whenever there is a charge entering into a node, that entering charge will be equal to the leaving charge. The entering charge will be equal to the leaving charge at a node. Entering charge will be equal to the leaving charge. Entering charge will be equal to the leaving charge. This is the Kirchhoff's current law. In other words, the algebraic sum of all the currents entering and leaving a node must be equal to 0. That is, I entering and I exiting. Those two will be equal. I entering will be equal to I exiting. That is, I entering plus I exiting equal to 0. This idea of by Kirchhoff is commonly known as the conservation of charge. We know that there are different types of conservation of energy, right? We know that there are different types of conservation laws. In that conservation laws, one of the law is called as the conservation of charge, where the amount of charge entering is equals to the amount of charge leaving. That is, whatever the charge that is being given will be the charge that is being taken out of the node. So this particular law is commonly known as the conservation of charge, which is nothing but the amount of charge entering into a node will be equal to the amount of charge leaving the node. This is the KCL. This also we This is the most fundamental law which we need to know, because if you don't know what is the amount of current entering into the node and amount of current leaving the node, we cannot judge how much of current is being circulated in that particular node. So, in order to understand what is the current circulated in that node, this is the fundamental law. The next law is called as the Kirchhoff's voltage law or KVL. This states that in a closed loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop, which is equal to 0. So what does this say means? The algebraic sum of all voltages Algebraic sum of all voltages within a loop must be equal to 0. So, if there are certain voltage drops in a loop and then there is a certain voltage rise in the loop, those two must be equal. That is what this law states. That is, if there is a source in that particular, okay, I'll just give you here, if you can see, here there are four resistors. The sum of all the voltage drops around the loop must be equal to 0. So, if you are adding up all these voltage drops, that should be equal to 0. That should be equal to 0. If there is a source in place of resistor, that source rise will be equal to the that source's voltage rise will be equal to the voltage drops of the remaining elements in that particular loop. Okay, that is the KVL, Kirchhoff's voltage law. This idea is known as conservation of energy. This idea is known as conservation of energy. The above idea, that is the KCL, is known as the conservation of charge, where all the currents entering a node will be equal to the currents leaving the node. That is the first one, Kirchhoff's current law. Now, the Kirchhoff's voltage law states that algebraic sum of voltages within a loop must be equal to 0. That means the voltage drops must be equal to the voltage rises. The voltage drops must be equal to the voltage rises within a loop. This idea is called as the conservation of energy. That is the conservation of charge, and this is the conservation of energy. This is the Kirchhoff's voltage law. Another most important law in order to analyze the circuits. Okay, so we have seen Kirchhoff's current law as well as the Kirchhoff's voltage law. So the next laws or the next set of laws which we will be tackling are called as the Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. So what is this Faraday's laws of electromagnetic induction? First we need to know, right? So here there is a definition. This Faraday's law of electromagnetic induction is a basic law of electromagnetism, predicting how a magnetic field will interact with an electric circuit to produce an electromotive force. So it is giving us the basic idea of how the electrical energy or the electromotive force is being produced in a magnetic field. By how the interaction is there between the magnetic field and the conductor, such that there is an electromotive force, that is the EMF is being generated. This phenomena is called as the electromagnetic induction. So the name itself indicates electromagnetic induction. By using the magnetic medium, we are inducing the electrical current. We are introducing the electrical current. Let us see what are these laws and how are they being depicted. So Faraday's first law. Okay, this is the Faraday has predicted two laws, and first law is this one. Any change in the magnetic field of a coil of a wire or a wire, not of wire, of a coil or wire will cause an EMF to be induced in the coil. This EMF induced is called as the induced EMF, and if the conductor is a closed, if the conductor circuit is closed, the current will also circulate through the circuit, and this current is called as the induced current. He is saying that if there is a change in the magnetic field of the coil or wire, okay, if we have a coil and the magnetic field of that coil is being disrupted, if the magnetic field of that particular coil is changed, then there will be an EMF induced in that coil. Then there will be an EMF induced in the coil. This EMF which is being induced is called as the induced EMF. And if the circuit is a closed loop, then there will be a current flowing through that circuit which is called as the induced current. Then there will be a current flowing through the circuit and that will be called as the induced current. So he's saying that you have to change the magnetic field of a coil. How to change the magnetic field of a coil? That is the next question, right? So he is giving us different methods to change the magnetic field. What are those different methods? Let us see. He's saying that by moving a magnet towards or away from the coil. So he's saying that if we just move the magnet towards or away from a coil, then there will be a change in the magnetic field of the coil, and then there will be an induced EMF induced in that particular coil. So that is the first method. The second method is moving the coil into or out of the magnetic field. So if you consider this as the magnet, now the coil is being moved towards and away from the magnet. In this manner also we can change the amount of magnetic field around the coil, right? So by either by moving the magnet towards and away from the coil, or by moving the coil into and out of the magnetic field, either way we can they change the magnetic field and an EMF can be produced. Next method is by changing the area of the coil placed in the magnetic field. By changing the area of the coil placed in the magnetic field. So let us say we have an even magnetic field. Then if I am changing the coil that is being exposed to the magnetic field. Let us say this is the magnetic field. If my right hand is the magnetic field and left hand is the coil. Now if this is a constant value, the magnetic field is a constant value. If the amount of coil that is being exposed to the magnetic field is being changed, okay, now even this can cause the change in the magnetic field of the coil, and then EMF can be induced. By rotating the coil, and the fourth method is by rotating the coil relative to the magnet. Okay, by rotating the coil relative to the magnet. If the magnet is there and the coil is being rotated. Similar way, okay. So these are the four methods in which the magnetic field of the coil can be changed and the EMF can be induced. Let us see these four methods in action. Okay, here you can see all the different four methods which we have discussed earlier. So in this first method, the coil is being held constant and the magnet is being moved towards and away from the coil, so such that the magnetic field is being disrupted and there is an EMF induced. In the bottom you can see a galvanometer which is showing us that there is a deflection in the current. How much, that is a different matter, but there is a deflection in the current. Here on the right hand side, top of your upper side, on the right hand side, you can see that the coil is being introduced into the magnetic field and withdrawn from the magnetic field, introduced into the magnetic field and from and taken out of the magnetic field. And at the bottom of that particular slide you can see that there is a EMF induced, and how the EMF is being changed is also being shown there. The next one is here, the magnetic field is being changed. The amount of coil that is being exposed to the magnetic field is being changed, such that we can see that there is a deflection, and that deflection is showing us that there is some EMF that is being induced. Here you can see that the coil is being rotated relative to the magnetic field. The coil is being rotated relative to the magnetic field. Here also we can see that there is a change in the EMF. The galvanometer is also showing us a little deflection when the coil is being rotated. So these are the four methods in which the Faraday's first law can be depicted. Faraday's second law. It states that the magnitude of the EMF induced in the coil is equal to the rate of change of flux that links with the coil. The flux linkage of the coil is the product of the number of turns in the coil and the flux associated with the coil. So the Faraday's first law gives us how the electromagnetic induction is being done. Faraday's second law gives us what is the amount of what is the amount of EMF that is being introduced. Amount of EMF that is being introduced. So this is the formula. E is equals to change in the flux, that is change in the flux linkages, that is d phi by dt, d phi by dt. And then if there are number of loops, that is if the coil is having number of loops, then that number of loops into the EMF, that is into the change in the flux, that is n into d phi by dt, n into d phi by dt, that is the amount of voltage that is being produced, that is the amount of EMF that is being produced. And here from this EMF you can find out the current also, that is I is equals to E by R, that is we know this, right? I is equals to V by R. This is the Faraday's second law. So the next concept is called as the induced EMF in a straight conductor. Now that we are taking a conductor and we are placing it into the magnetic field and we are rotating the conductor in the magnetic field and all those things, we are just looking at the formula for the induced EMF in a conductor. So here on the right hand side you can see a diagram which is depicting how the coil is being placed and what is the angle of the coil relative to the magnetic field, and what is the amount of EMF that is being induced in this particular coil is given by a formula BLV sin theta, where B is the flux density of the magnetic field. What is the how much amount of flux is present in a particular, in a unit area, is called as the flux density, which is measured in Tesla, that is B. And then L is the length of the conductor. L is the length of the conductor, the total length of the conductor, okay, that is being exposed to the magnetic field. And then V is the velocity at which the conductor is being moved. The velocity at which the conductor is being moved. And then theta is the angle by which the conductor cuts the magnetic field, the inclined angle of the magnetic field. The inclined angle of the conductor to the magnetic field is called as the theta. So E is the induced EMF in volts. So this is the formula, that is E is equals to BLV sin theta. So where the maximum amount of flux linkages will be cut means when angle theta is equals to 90 degrees, sin 90 is equals to 1. So E is equals to BLV. E will become equal to BLV, where B is the flux density, L is the length of the conductor, V is the velocity at which the conductor is moving. So at theta is equals to 90 degrees, maximum amount of flux will be blocked or will be cut by the conductor, such that there will be maximum amount of EMF that is being produced in that conductor. So this is the induced EMF in a straight conductor. This formula is also quite important for us because this will give us how much of amount of voltage will be induced in a conductor. So the next topic which we will be seeing is the Maxwell's right hand thumb rule. We are saying that there is a magnetic field around the conductor and we are saying that that magnetic field is being disrupted and all those things, right? So first of all we need to understand what is the direction of this magnetic field around the conductor, right? That direction of the magnetic field around the conductor is given by Maxwell's right hand thumb rule. So what does this state? Let us see. If you are holding a current carrying a wire in your right hand such that the thumb points in the direction of current, then the direction in which the fingers wrap the wire represents the direction of the magnetic lines of force. So if he is saying that if there is a current carrying conductor, let us say this is the current carrying conductor. Now we have to place this current carrying conductor in our right hand, and then we have to make sure that our thumb is representing the direction of the current. That is, if I'm assuming that the current is flowing in the upward direction, then my thumb is giving me the direction of the current, and now the curl of the fingers, the curl of this fingers will give me the direction of the magnetic field. Will give me the direction of the magnetic field. So let us see. Here is in this diagram itself, he is showing us how the current will be and how the direction of the magnetic field will be. When the position of the thumb will be upward, the curled fingers will be anti-clockwise. So if the position of the thumb is upward, then the curled fingers will be anti-clockwise. Anti-clockwise. And if the and the magnetic field will be, and the magnetic field be and the magnetic field will be in this direction only, no? Okay. Hmm. Anti-clockwise. That's all. This sentence is a little wrong. So if the curled fingers are in this, what do you say? And are in the anti-clockwise direction, so the magnetic field will also be in the anti-clockwise direction. Similarly, when you are holding in the opposite direction, that is, if the current carrying conductor is the current is in the opposite direction, then the curl will be like this, and then the magnetic field will also be in clockwise direction. So this is the Maxwell's right hand thumb rule. So the next law which we will be seeing is called as a Lenz law. Lenz law is a very important law. Here it will give us the direction in which this EMF is being produced. Why is this? What is the nature of the EMF and how this direction is there? That will give us, that will be given by the Lenz law. Lenz law of electromagnetic induction states that the direction of the current induced in a conductor by changing a magnetic field is such that the magnetic field created by the induced current opposes the initial changing magnetic field which produced it. So basically, this is like the Newton's third law. Okay, it is like every action has an equal and opposite reaction. So always the reaction will be opposite to the original action. That is the Newton's third law, right? In the similar way, here also, if we are saying that there is a current carrying conductor, sorry, if there is a conductor and we are changing the magnetic field of the conductor, we know that whenever we change the magnetic field of a conductor, an EMF is being induced. But this induced EMF, the direction of the current because of this induced EMF will be such that it will be always opposite to the original source. That is, if whatever may be the source, that is, here you can see, if we are taking a not we are taking a magnet and then we are moving the magnet towards a conductor, then the side of the then the direction of the current in on that particular side of the conductor will be exactly opposing the original conductor. That is, here if you can see on the left hand side, on the bottom of your page on the left hand side, here you can see that a north pole and south pole is being a magnet is being moved. So in this magnet, when the south pole is near to the conductor, when the south pole is near to the conductor, here when the south pole is near to the conductor is walking again as south pole. The conductor is acting again as south pole, so that these two will be opposite. Now if you just move the magnet away from the conductor, if you're just moving the magnet away from the conductor, here now it is moving away, so the conductor is trying to attract the magnet. If the conductor is trying to attract the magnet, so if the magnet is moving towards the conductor, it is trying to oppose it. But if the magnet is moving away from the conductor, it is trying to attract it. That means whatever might be the situation, whatever might be the case, whether it is moving towards it or away from it, it always opposes what is causing it. That is, if the magnet is moving towards the conductor, then the conductor will oppose it. If the magnet is moving away from the conductor, then it will try to attract it. So whatever might be the action, it will give you an opposite reaction. Whatever might be the action, that will give you an opposite reaction. So here the magnet wants to go towards the conductor such that then the conductor is opposing it. The conductor, the magnet is trying to get away from the conductor, then it is trying to attract it. So this is the Lenz's law. Because of this opposition nature, what happens is the voltage which will be produced will be associated with a minus symbol, because it is always opposite to the opposite to the source. So we are representing the voltage which is being produced in the conductor as a negative value. That is why here we are getting a minus symbol. E is equals to minus n into d phi by dt. E is equals to minus n into d phi by dt. So this is the Lenz law. Next is Fleming's right hand rule. We are saying that there is a conductor, and when the conductor is being changed, when the direction of the when the magnetic field of the conductor is being changed, there will be an EMF produced and all those things, right? But what is the direction of this EMF produced is given by the Fleming's right hand rule. The direction of the induced EMF in a conductor in a magnetic field is given by the Fleming's right hand rule. When the forefinger, thumb, and the central finger of the right hand are stretched perpendicular to each other, then if the forefinger represents the direction of the magnetic flux, thumb represents the direction of the motion of the conductor, and then the central finger represents the direction of the induced EMF. So he's saying that uh, if we just stretch our left three fingers of your right hand in such a way that they are perpendicular to each other. Now he's saying that if the forefinger represents the magnetic field, if the forefinger represents the magnetic field, and thumb represents the motion of the conductor, and thumb represents the motion of the conductor, then the central finger represents the direction of the current. The central finger represents the direction of the induced EMF. So this by using this Fleming's right hand rule, we can understand what is the direction of the induced EMF. So this, why are we specifically saying that it is induced EMF means, because if the circuit is not closed, then there will be no current flowing in through the total circuit, right? So the EMF will be induced even if the circuit is not closed. The EMF will be guaranteedly induced. That's why we are saying that the central finger will be representing induced EMF. Okay, if this comes in a multiple choice question, if he asks you in this in a multiple choice question, then you have to first look for the induced EMF. If the induced EMF is present, go for the induced EMF. If induced EMF is absent, only then go for the current option. Okay, if the options give us an induced EMF, then go for the induced EMF. If there are no option, if there is no option like induced EMF, then go for the current. That's current will be your second choice, not the first choice. Okay, so Fleming's right hand rule, it gives us the direction of the induced EMF in a conductor which is placed in a magnetic field. Okay, so here where again let us see, if the forefinger represents the magnetic flux, if the forefinger represents the direction of the magnetic flux, and thumb represents the direction of the motion of the conductor, then the central finger represents the direction of the induced EMF, or current, the direction of the induced EMF or current. This is the Fleming's right hand rule. This is the basic rule which will give us the direction of the induced EMF, and this is used in generators. To understand what is the direction of the induced EMF or current in a generator, we will be using Fleming's right hand rule. So then there is another rule which is called as the Fleming's left hand rule. The Fleming's left hand rule gives us the direction of the motion of the conductor in a magnetic field. If there is a conductor placed in a magnetic field, then in which direction does this conductor move will be given by the Fleming's left hand rule. Here also we need to make sure that our forefinger, thumb, as well as the central finger of the left hand are stretched perpendicular to each other. If the forefinger represents the direction of the magnetic field, if the forefinger represents the direction of the magnetic field, and the central finger represents the direction of the current. If the forefinger represents the direction of the magnetic field, and central finger represents the direction of the current, then thumb represents the motion of the conductor. Then thumb represents the motion of the conductor. So this is how, if the forefinger represents the magnetic field and central finger represents the direction of the current, then thumb represents the direction of the motion of the conductor, the direction of the motion of the conductor. So this is Fleming's left hand rule. Fleming's left hand rule. This Fleming's left hand rule is being used in motors. In order to understand what is the direction of the mechanical energy that we are going to get from a motor, we will be using Fleming's left hand rule. For the direction of the current that is being induced, we will be using Fleming's right hand rule. Whereas in order to understand what is the direction of the motion of the direction of the mechanical energy which we will be getting, we are using Fleming's left hand rule. Okay, so these are the fundamental laws which are required for understanding the basics of the machine, how the machine will be, and how the uh, direction of different parts will be, and how to understand the machines. These are the basic fundamental rules. So let us just summarize what we have seen in today's class. Basically, we have seen what is a generator. Generator is a machine which converts mechanical energy into electrical energy, and opposite to this generator, we have a machine which is called as a motor, which will be taking electrical energy and converting it into a mechanical energy. Both these conversions take place in a magnetic medium. Both these conversions take place in a magnetic medium. So, in order to understand all these concepts, we are going to see some fundamental laws. These are the main fundamental laws for any machine. That is, first one is called as the Ohm's law. The next are the Kirchhoff's laws. Next is Faraday's laws of electromagnetic induction, Maxwell's right hand thumb rule, Lenz's law, Fleming's right hand rule, and Fleming's left hand rule. So Ohm's law gives us the relation between the voltage and current, and the total Ohm's law can be represented by using one equation, that is V is equals to IR. V is equals to IR, where V is the voltage, I is the current, and R is the resistance. Okay, next is the Kirchhoff's laws. We have two Kirchhoff's laws. Kirchhoff's current law, which is called as the KCL, which is also known as the conservation of charge, which tells us the amount of charge entering into a node is equals to the amount of charge exiting the node. That is the Kirchhoff's current law, KCL. And the next one is the Kirchhoff's voltage law, which is called as the KVL, or the conservation of energy. Here, if you are taking voltage rises in a loop, that will be equal to the voltage drops in a loop. Voltage rises is equals to voltage drops in a loop. Next is the Faraday's laws of electromagnetic induction. It is giving us, Faraday has stated two laws. The first law is giving us that any change in the magnetic field of a coil will cause an EMF to be induced in the coil. Any change in the magnetic field will give us a change in the induced EMF. So these are the different methods in which the EMF can be induced. We have seen all four different methods. Next is Faraday's second law, which gives us the amount of EMF that is being produced. That is nothing but amount of EMF that is being magnitude of EMF that is being induced is equals to the rate of change of flux linkages of the coil, that is d phi by dt. If we have n number of loops, that is n into d phi by dt. Next is induced EMF in a straight conductor. This is an equation. E is equals to BLV sin theta, where B is the magnetic flux density, L is the length of the conductor, V is the velocity of the conductor which is moving in the magnetic field. Theta is the angle by which the conductor is cutting the magnetic field. Next is Fleming's right hand thumb rule. This gives us the direction of the magnetic field that is being produced around the coil. If you are assuming a current carrying conductor in your right hand and the thumb is representing the direction of the current, then the curl of the fingers will represent the direction of the magnetic field. Next is Lenz's law. Lenz's law is similar to what we have seen in the Newton's third law. Always the reaction will be opposite to the action. So whatever the induced EMF is produced, in whatever is causing the change in the magnetic field, that change will be opposing the original cause. Okay, this is the lens zone. Next is Fleming's right hand rule. Here, the direction of the induced EMF in a conductor can be found out by using this Fleming's right hand rule. So, the forefinger represents the magnetic flux, thumb represents the direction of the conductor, the central finger will be representing the direction of the induced EMF or current. So, this is Fleming's right hand rule. Similarly, this Fleming's right hand rule will be used for generators. And then we have Fleming's left hand rule. Here also forefinger represents the magnetic flux and central finger represents the direction of current. And when this is happening, the thumb is representing the direction of the motion of the conductor. This is used in motors.